Hello, welcome back to the office setting again. And today we'll continue looking at some computer basics. We'll talk about floating point numbers. And if you look on the slide, you'll see that the floating point numbers is marked with a star or an asterisk, as it's supposed to be called. And this means that this is sort of optional material. And for you, that means we'll tell you something today that many practicing scientists, even computational scientists, probably have heard of, but they don't know. So that's why it's optional. But it's good to know. Makes you realize why some of the rules we give you come about. They don't come about because we like you to follow rules and we just like to be commanders, but rather there's a real purpose, and this is where they come from. So recall floating point numbers. That's just a fancy way, maybe not so fancy, another way of saying scientific notation numbers. And most scientific calculations employ floating point numbers. There are integers. There's nothing wrong with integers. They're used all the time for things like counting, how many times you repeat an operation, or specialized work, like I said, cell phones, where they have to be very fast, but you don't have large ranges. For scientific work, where you have a finite range, you want to use floating point numbers. So let's get on. Let's look at slide 2. Okay. So this is the IEEE standard for how floating point numbers work. And remember, IEEE means, I don't know, the Institute for Electrical and Electronic Engineers. So it really has very little to do with engineering, but they've written down some standards for how numbers should be stored on the computer, stored in a way so that if you use different computers, even different computing languages, you should always get the same answer. So what we have up here in equation 1 is the representation used. Look at equation 1. It's pretty complicated. The thing of interest is that you don't have to tell the computer about this equation. The computer knows this equation. And all you give the computer when you store a number is not this format. It knows this format, but you give it instead the values of the sign bit S, the values of the mantissa F, and the values of the exponent E here. Okay? So, as we've seen, the number out in front, S, is the sign bit, because really it's -1 raised to this power S. So if S is 0, we get a positive number. If S is 1, we get a negative number. So 1 bit out of the whole word, say a 32-bit word, is used to store the sign. You always need that. Then comes F. F is sort of the mantissa, but it's not the whole mantissa, although sometimes it may be called, that's where we store the mantissa, because in general we try to store on the computer with this IEEE notation 1 point F. So the number 1, the binary number 1, occurs before not the decimal point but the binary point there, and then F is the mantissa stored as a binary number. Okay, so F stands for, if you want, the fractional part, as a reminder that the whole integer part 1 is out in front. Okay, so by having this extra 1 out in front, actually you get another bit of precision for most numbers. So these IEEE engineers are really pretty clever the way they figured this out. Okay, the advantage, as we've said, of IEEE arithmetic is that it tends to give you the same relative precision for all numbers stored in this format. So even if the number is big or small, you know relatively what the error is like. Okay. So now E is the exponent. So E is stored up here. So you have 2 raised to some power, E, minus a bias. So it's not the regular exponent that you store when you write a scientific notation number, but rather it's set up so that you never store a negative exponent on the computer. So you always subtract some large number bias, but you, when I say you, I don't mean you personally. I mean the computer does that. And the computer knows what the bias is because these IEEE engineers have told them what it has to be. And it just automatically subtracts bias. So if you have a number which is less than the bias being subtracted, so if that's the exponent that you've stored, then when you subtract the bias, you get a negative number. So the mathematics works out okay. You can store negative integer exponents, but they're stored in the format of only a positive number. And likewise, the true exponent, P, can be less than 0. But the actual stored exponent is always greater than 0. Now, there's several types of IEEE numbers. By and large, the main kind you deal with are normal numbers, and these are numbers which range have an exponent in the range from 0 to 255. But this less than sign, no equal down there, means that 0 to 255 are allowed, but they're not normal. Those are abnormal cases. So if the value of the exponent, and it's not the real exponent, p, it's just what's stored as the exponent. So if this value of the exponent is 0, or the value is 255, then we have special cases. And the special cases are covered in the next slide on the next transparency. So let's look. So this is slide 3. Look at it, please. Have you memorized it all now? Not to worry. You don't have to memorize any of this stuff. What we want you to do is look at it, understand where it's coming about. What you see on the first line of this slide is what we've just told you already. Normal numbers have this exponent stored for the biased exponent in the range 0 to 255, and this is the IEEE format used for it. Subnormal numbers are those numbers for which the exponent is 0 and the stored fractional part of mantissa, f, is non-zero. Okay? So for those numbers, then the number is stored in this format with a 0 out in front and an exponent lowered by 1 power. So it doesn't change the range and the continuity of numbers, but it's the way the numbers are stored in order to have them continuous, in order to have the same relative precision. Now we have some special cases, and they're actually quite interesting. So first question is, what if e, the exponent stored is 0, and the mantissa, the fractional part, f, is also 0? Normal thing, you'd say, aha, that's obviously a number that's 0. Well, that's true in some sense, but on a computer you can store 0 in 2 different ways, mainly because we still have the sign bit out in front. So there's a positive 0 and there's a negative 0, and the two are stored differently, and sometimes they're used for purposes. Often I've seen, probably all too often I suspect, a computer program come back with 0 minus as an answer as a way of telling you, hey, you've done something wrong, I'm quitting, I don't like you. So there's reasons to have that. There's other special cases. If you have the sign bit 0 and you have an exponent 255, so that's the maximum exponent, but the fractional part is 0, f is 0, that's how the computer stores what it calls plus INF. And that essentially means plus infinity. But don't feel good about plus infinity. This is sort of a computer scientist plus infinity. If you're a mathematician, you do mathematics, even if you don't call yourself a mathematician, you realize there's lots of different kinds of infinities, and sometimes in mathematics you might be able to divide one infinity by another, come out with a finite number. These infinities on the computer are not that kind of infinities. They're just a symbol written, as it says here, as INF, written to mean it's a computer's telling itself this number is plus infinity. You can't deal with it. It'll print out as plus INF. If you multiply it by anything else, the computer usually will quit and be unhappy. If you have a sign bit of 1, but still maximum exponent and 0 fractional part, then you get minus infinity. It's what the computer calls minus infinity, but it's not a real mathematical minus infinity. And finally you get another type of bad number, a number that you don't want to see in your computer calculations, and it's called NaN for not a number. So you really can't get a number because it's not a number, but it is a number. And I didn't make up the rules anyway. So if the sign bit S is 1 and the maximum exponent is 255 and the fractional part is non-zero, then you get a funny kind of number. You get not a number. It's the computer's way of telling you, I don't know what you're talking about, and we shouldn't go any further than this. So we've said enough about these special cases. Let's look at slide 4. Slide 4 gives you some of the details, and this is where the understanding is about. And here we'll look, for the rest of this lecture, for everything I tell you about, we'll only look at single precision numbers. So they're single precision floating point numbers. They're often called floats on the computer. As you know, and I've warned you at least twice, probably 3 times now, you shouldn't even use floats. You should ever, when you do a calculation, you should always use double precision or doubles which are floating point numbers, they're just twice as big. But if we had to tell you about everything in the double, it would take twice as long and be twice as boring. So let's just talk about singles, and the rules will be very similar, just the numbers change when we talk about doubles. So here on top, you see this table, and this table represents one 32-bit word on the computer. So there's 32 bits kept together in memory. It's called a word. And on each column here, each box has a different position on the word. And we start off with the first bit, except we talk like computer scientists, and they don't start counting at 1, they start counting at 0. Mathematicians, physicists usually start counting at 1 and go up. This is what happens in multidisciplinary fields. Sometimes we'll write down mathematical equations starting at 1 for a subscript, and when we translate it to the computer starts at 0. So you have to be careful. You always have to be careful, but it can matter. So here we have a 32-bit word. The first position, or the 0 position, to the 22nd position is where the fractional part is stored, F. Okay, and that's, how many bits is that? It goes from 0 to 22, so that means 23 bits. Okay, so most of the word, most of this 32-bit word is stored in the mantissa. That's because this is sort of a balance to do as well as we can. The biased exponent here, the biased exponent is stored in bits 23 to 30. So that's 8 bits, okay, and that's all. So the exponent has a smaller range of values than the fractional part of mantissa. That's fine. And that lets us store exponents in the range from 1 to 254. So that's power 2, 2 to the power 1 to 254, essentially is all we can do. But with the bias, and in this IEEE format, when we're dealing with 32-bit words, the bias is usually 127 to base 10. So I'll mix together here. We store the words in binary form, but when we talk about their sizes, we always talk about base 10, the decimal system. So for bias is 127, that means the actual exponents we can store will be E converted to base 10 minus 127. Okay, so that puts the P, the actual exponents, in the range minus 126 to 127. We'll talk more about that later. You'll see this number come about. Now you know why it comes about. So what have we done? We've said 23 bits go into the fractional part, 8 bits go into the exponent, and 1 bit, the 31st position, because that's the 32nd bit. Oh, I don't like computer science sometimes either. Anyway, 31st position goes to the sign bit. Okay. Then there are the special cases. So for all of the normal cases, we use the standard IEEE format with a 1-point F, and for these special cases, we use the other format with a 0 out in front, or special signs. So we talked about those. So let's look at an example. Okay? So take a look at slide 5. This is an example when we ask you to compute the largest normal 32-bit float that can be stored on a computer. This is what we have to do. Well, it's sort of obvious. We say, what's the largest 32-bit? Well, number. Well, first you'd make the exponent E, that stored exponent, as large as possible. It has the maximum value 254, and that means the actual exponent, which is E minus 127, is 127. So that's the maximum exponent it can have. The sign bit can be 0 or 1. Let's say it's 0, so it's a positive number. If it was 1, it would be a negative number. It would be, if you're a mathematician, you'd say it's the smallest number. Computer scientists might say it's the largest negative number. Okay. Equation 3 shows us what's the largest F, fractional part of the mantissa you could have. Well, the largest number in a binary system would be when all the digits are 1. They don't have much choice. It could be 0 or 1. 1 is the largest. So this, and I can't count very well, but you know, if we start counting with the spaces, there's 4, 8, 10, 12, 16, and then 3 here, 19. You know, we have 20 there. That's the biggest F value we can have. And if you convert all of this value of F into a decimal number just by working out what the conversion is, which I do on equation 4, You see that it's 1, there's the 1, then the other bit gives you 0.5, then 0.25. You add it all together, you get a number very close to 2. And that's right. If it was a little bit bigger, it would be 2, and it's not quite 2. So when we're done, this the largest 32-bit number comes out to be about 2 times 2 to the 127th power, and if you convert that to decimal, you see it's about 3.5 times 10 to the 38th. And that's what you see in the tables. You always say, oh, what's the largest range? This is the range it lies in. Okay, so that was work. You know, these kind of details are tiring. They're not intellectually exciting in any sense, but they are sort of interesting because this is how the world is done. This is how computers store a number in the most elementary way. You probably didn't understand everything I said, which is fine. The only way to learn this stuff is to start using it. So now let's go to a lab and let's try to do some exercise in the lab and see if you can make sense in the lab for what's going on. Okay, so here we look at IEEE representation, how floating point numbers are stored. We want you to do this by hand, at least for the exercise. Ultimately, you let the computer do all this, but it has to get through your brain somehow once, and you're not going to just get it through your brain by looking at it. You have to process it some way. So here I give you a 32-bit single precision floating point number. That's a lot of words. What does it mean? 32-bit means that's how many bits the computer's using. It's obviously single precision. Single precision means it's single precision because all 32 bits, well, they could be integers. So it's a 32-bit floating point number. And floating point number means that the exponent and the mantissa are stored separately. So here's the number. So in this table, again, we've broken up what would be one word on the computer into 3 chunks. And the computer languages, operating systems, they're smart. They know this is how words are broken up. So all you store is, again, the floating point part, or the fractional part of mantissa, the exponent, and the sign bit, and in bits numbered from 0 to 31 for a total of 32 bits. Okay? So the first question for you to answer is, what are the binary values for the sign bit S, for the exponent E, and the fractional part F? So go back to what we just spoke about, or in the notes, or in the book, which you should all go out and buy a copy of if you haven't yet. Tell me what they are. I'll give you a hint here. The sign bit S is 0. And it's 0 in binary. It's also 0 in decimal or octal. 0 is 0 in everything. The exponent, now you have to work some numbers out. Okay? So, but these are the binary values, so this is easy. That's exactly what you read here. So you just copy it down, but don't tell your instructor I told you this. Okay? What are the decimal values? Now you have to do some conversion. Okay, so what's the decimal values for the sign bit? I don't even ask you that. It's still 0. Zeros don't change. Everyone agrees on 0. For the actual exponent, you have to subtract the bias. What's the bias? Go look it up. Okay. Here, unless I made a mistake, and that has happened, but I don't think I did here, show that when you're done here, the actual mantissa of the number is 1.625,000,000. And finally, what's the decimal value of this number? Okay. So if you've done this, say you've done enough. You don't have to do any more of these. This is a normal number. You know how the system works. If you get real ambitious, and some students have, they've actually gone into the computer and have the computer print out exactly what's stored in memory here and identify the parts. That's a wonderful thing to do, but that's hard. And we'll talk about that soon, why it could be hard. So, okay, now, what other important aspects occur with floating point numbers? Well, they occur with integers too, but in different ways. But basically what I've kept telling you is we only have a finite number of digits used to store a number. Single precision, 32 bits, doubles, 64. And that means if the number gets too small in the exponent, or too large in the exponent, there's no place to store it. And when it gets too large in the exponent, that's called an overflow. When it gets too small, that's called an underflow. We spoke about that last time. Overflow is obvious. It's just there's too many numbers to fit in a small space, they overflow someplace else. So what we want you to do in the lab is to determine experimentally the underflow, overflow limits of your computer. Let me tell you, when I say experimentally, I mean think of this as a scientist. Don't think of this as I've memorized what he's told me, I deserve an A, I'll repeat everything he says. No, don't believe a thing I say. Prove it to yourself. See what your computer does, see what your computer language does, because who knows, you may be running this 20 years from now and the computers will be different. They may give you different answers. The ideas won't change, but the computers may change. Your computer may not be working right. The only way you know is to try it. And when you try something, you're trying to what's technically called break the computer. Okay? We want you to do something so the computer breaks. It doesn't work the way it should nicely, and then you see what happens when the computer breaks. You learn what happens, and you learn how to fix that. So what I've told you here is if you have an overflow, and we're using this IEEE format, then the largest single precision number you should be able to store is 2 to the power 128. Figure that out in decimal on your own. And the smallest should be 2 to the minus 128. So what happens if a number gets smaller than this? That's for you to see. You get what we would call an underflow. If a number is bigger than that, you get an overflow, but you need to see what the computer prints out. Okay? It could print out sometimes NaN, not a number, sometimes infinity. You need to see. There's no reason for me to tell you. And I want you to do this exercise, please, both for singles and doubles, so those two floating point numbers, and then for integers, and both positive and negative integers, and to see what happens when they get too big and too small. So, on the bottom of Lab 2 slide here, we give you some pseudocode. And pseudocode is not any particular computer language, just sort of a general scheme of how you understand, how you write a program, how you understand what's going on. So what this says is, let's start off by initializing some variables. Let's call them under and over. So under is we start at 1, over we start at 1. And then all we're going to do is just keep dividing under by 2, which is what we do here in the loop, and we'll keep multiplying over by 2 until the computer starts complaining. Simple as that. So here we say begin a do loop. You can use a do loop, a for loop. It just means repeat everything here indented n times, where n is capital N, some large number. How large a number, you ask? And I tell you, I don't know. It doesn't matter. If it's not large enough to give the effect, then make it larger. If it's too large and you can't go home at night because the computer's still running, make it smaller. That's what experiments are about. They mean you're supposed to fail some of the time. Okay? And each time you go through the loop, write down, have the computer write out, in other words, the loop number, the current value that it's gotten to, not capital N yet, some number smaller than that, what the value of underflow and what the value of over is. And then you're done. Okay, so you write a program in your favorite language that does something like this. And it's a program you might keep with you for the rest of your life, along with the next one or two, because any machine you're on, any computer language, you want to know, regardless of what the authorities tell you it should be doing, you want to know what it's doing. That's how you learn. You know what? I think you should get to work now, and then we'll do some more work in the lab. Bye-bye.